It's great to be back at the European Symposium on Algorithms to present our paper, Competitive Auctions and Multiple Digital Goods, 20 years later. To put you in the mood, I went in the Wayback Machine and found some old photos of Andrew and I from back in that era. And some context for what was happening around the time of this paper. So, algorithms researchers had just gotten interested in understanding how to design good algorithms when the inputs to the algorithms could come from strategic agents that may manipulate the input to try to get the algorithm to produce a more favorable outcome to them. Nissan and Ronin, a few years before, had published their algorithmic mechanism design paper, primarily studying algorithmic questions in scheduling. Lehman, O'Callaghan, and Shoham had published their paper on combinatorial auctions and looking at greedy algorithms. And earlier in the year, Andrew Goldberg and Andrew Wright and I had published our first paper on uh, using tools from online algorithms to study revenue maximization in auctions. So what did this paper do? The paper defined an algorithmic pricing problem. And in this problem, we are given a bunch of buyer preferences for multiple items, and we're trying to compute prices to maximize the revenue of the seller. It gave a random sampling-based reduction from the mechanism design problem to the algorithmic pricing problem. So it says that if we can solve this algorithmic pricing problem, then we can convert the solution into a mechanism. And the key issue here is that we can't just run the optimal pricing algorithm, as the buyers might try to, manipulate their preferences to then get lower prices. And so we really need a mechanism to ensure that we're getting a good outcome, even when buyers might be strategic. And then the final ingredient is a sample complexity analysis to show that this random sampling-based reduction works well. And essentially what we have to do here is show that prices that we compute for some sample of the bidders are going to be pretty good prices for revenue on the remaining bidders. Okay, and what I think in hindsight is really useful about what we did in this paper is it decomposed this mechanism design challenge into two problems, and both of these problems ended up being really quite interesting. And the first problem is this algorithmic pricing problem of coming up with algorithms to compute prices to get good revenue. And the second question is this sample complexity problem of understanding how well good prices generalize from a sample of the population to more draws from the same distribution. Okay, so to overview the talk, I'm going to start by going into some of the details of what we did in this paper, and then I'm going to spend a lot of time talking about what the subsequent literature did for each of these research directions of algorithmic pricing and sample complexity. Cool. So what was the algorithmic pricing problem we were looking at? So we have multiple items, we have unit demand agents, and we have unlimited supply. Okay, and so a good example to have in mind is, we're trying to sell a movie on demand on an airplane flight. The flight's 3 hours long, so you have exactly an opportunity to watch one movie. And we can, give, any set of people the same movie. We can give people no movies, etc. Okay, so there's multiple items, multiple movies we can show you. It's unit demand. You only want to watch one movie, and we have unlimited supply, so everyone can watch the same movie if they want to. Okay, so n buyers, m items. Values will either be 0 or in some multiplicative bounded range. We'll let Vij be the value of buyer I for item j. We'll let Pj be the price that we're going to offer for item j. This is the thing we're trying to compute. And buyer i's utility for item j is going to be the difference between their value and the price. And the buyer aims to maximize this utility. And they'll choose their favorite item under this utility or no item if they're all negative. Our goal is to compute prices to maximize the revenue. Okay, so here's a picture. So buyers I've drawn as points in space where this is for the m equals 2 case of 2 items, um, and a point in space saying that's the buyer's value for item 1 and for item 2. And then prices you can see as vertical lines where the buyers above the line for item 2, the price for item 2, all are happy to buy item 2, and below don't want to buy item 2. And the buyers to the right of the price for item 1 want to buy item 1, and they don't want to buy item uh, and 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 the buyers to the left don't want to buy item 1. And then, of course, there are some buyers who are willing to buy both items, but they have their preferences. So they prefer to buy the item that gives them the highest utility, which is the difference of the value to the price. And so you see that for example, that the buyers that buy item 2 are the ones that are above this line and above the diagonal. Okay. And again, our goal is to compute, in this pricing problem, we want to compute the prices that maximize the total revenue. What is the total revenue? It's the number of buyers who buy item 2 times the price of item 2, plus the number of buyers who buy item 1 times the price for item 1. Cool. So we gave a random sampling-based reduction to construct a mechanism from such an algorithm. How did we do that? We randomly partition the agents into two groups A and B. We compute the optimal prices for group A and offer those prices to group B, and vice versa. And the main thing that's interesting about this algorithm is that this auction is truthful, meaning it's a dominant strategy for every agent to truthfully report their preferences. So why is that? Well, the agent's bid do not affect their own prices, and the way that the mechanism assigns the bidder an item is by looking at which, for the prices they're offered, which item maximizes their preferences. And the way to get the right item is by truthfully reporting your value. Cool. So then we wanted to show that this approach works well. So we had to do a sample complexity analysis. And what we showed was that if the optimal revenue is large enough in terms of the parameters of the problem, then the random sampling auction is a constant approximation of the optimal revenue. Okay, and what are the main proof ideas here? The first step is to bound the number of possible sets of winning bidders that are induced by prices. And so here's what I'm talking about. Um, Here we can see two gray regions that show the sets of bidders that are buying item 1 and item 2 respectively. And one thing to note here is if I jiggle around the price a little bit, these sets don't change. Okay, and in fact, each set is given by a signature, which is the points on the lower boundary or on the lower boundary of the set, and there are m points in the signature, which mean they're at most n to the m such sets, and that's good because if there's a small number of sets, if we can argue that all the sets are sort of roughly balanced, then we're good. Okay, and so that was our goal, to use Chernoff bound and union bound to show with high probability these winning sets are big, and then they're approximately balanced, meaning, for example, look at this set at the top for item 2. With high probability, roughly half of these buyers are in set A, and half of these buyers are in partition B. Okay, and if that's true, again, if all big winning sets are approximately balanced, then the revenue of any pricing on group A is going to be approximately the same as that same pricing on group B. Cool. Okay, so that's what we did in the paper. I'm now going to turn to going over some of the really salient works that are in the subsequent literature on both algorithmic pricing and on sample complexity. Okay, so the problem we posed in this paper was to compute the optimal prices in polynomial time. We left this as an open problem in our paper. Uh, After us, it was shown that if the number of items is a constant, there's a near linear time algorithm for computing good prices. And in general, there's a log n approximation, and really fantastic work showed that this log n was tight under some standard computational complexity assumptions. And if you wanted to write the bound in terms of the number of items, then even a linear bound was a linear lower bound was not uh, achievable. So that's a bit of a downer. And so actually a really nice work showed that one way out might be to, instead of pricing the items, we could price lotteries over items. In other words, so randomizations over items. So we could pick some, probably distribution of items and put a price tag on that, pick another one and put a price tag on that, et cetera, come up with a whole menu of these lotteries at different prices and optimize that instead of optimizing item prices. Okay, and amazingly, this is solved by a linear program. And so here's the idea. What we're going to do is we're going to come up with a lottery for each agent. Okay, and so we'll denote that by QI and PI, where QI is a distribution over items that's in agent I's lottery, and PI is the price we're going to charge agent I for this distribution over items. And then we write our objective as a linear program where we're trying to optimize the sum of the prices of all the agents, subject to the constraint that each agent wants to buy their own lottery, they're happy to buy their own lottery, and that these lotteries are actually lotteries. Okay, and so just zooming in on this first constraint here, this is saying that agent I prefers to buy their own lottery. So here we're writing out the dot product of the values and the probability vector of the lottery. So that's the surplus that the agent gets for this lottery minus the price they pay. That's the utility they get for this lottery. And we want to say they prefer their own lottery over anyone else's lottery. Okay, and look, this is a linear program with a quadratic number of constraints and number of agents, and so it's Polynomial time solvable. Okay, but item pricing is so natural, and lottery pricing is kind of complicated, and so there was a subsequent question of, well, how far apart can these optimal lotteries be from the optimal item pricing? And amazingly, even when the number of items is small, like 2, uh, the, you know, as you let the support of the distribution over buyers grow, I mean, letting the number of buyers go to infinity, this ratio can approach infinity. And this actually generated a really, rich current literature on what's called menu complexity, trying to understand the separation in performance in terms of the objective, revenue, in terms of how complex the menus are that we offer the agents. Okay. Um, so we just saw that there could be a really big separation between item pricings and lottery pricings with general distributions. and and this sort of motivates the perspective of, so I mean, and on the previous slide, sort of the input was essentially um, the uniform distribution over n different buyer types, because we're posting prices and our revenues, the sum of the revenues from all these different agents, that's the same thing as we have one agent who's one of these n agents at random, and we're offering a price. So this is just specifying a uniform distribution over n possible preferences of the agent. Um, and then once you have this perspective, you can ask the question about, okay, what about other kinds of distributions? If we have a distribution over buyer preferences, what is the pricing that maximizes the revenue? And here, a very natural special case to look at is the case where the distributions are independent across the different items. Okay, and so the previous setting obviously is a correlated case, and if we allow if we assume the distributions are independent, then there are other results possible. And so we showed two approximation for item pricing in the independent case, uh, and there was subsequently a time approximation scheme for the item pricing case, and the separating the item pricing from optimal lottery pricing was shown that they're within a factor of 4 of each other, which is really quite different from the correlated case that we saw could be unbounded. Another really awesome direction that this literature took was, so this is, again, for this, unit demand item pricing problem. Uh, and another direction that the literature took was looking at generalizations on unit demand. So we allow the bidders to maybe have additive demand or submodular demand across a set of items. And there's been a really excellent literature starting with Babayoff et al. Showing that simple mechanisms are approximately optimal in this scenario. They considered bundling or selling separately. So either we put price tags on each of the items and the buyers are additive and they'll buy whichever items they want, or we bundle all the items together and only if the buyer's total value for all the items exceeds the price for the bundle of items are they going to want to buy. And so this paper showed that one of these two mechanisms is approximately optimal. And as I said, there's a huge line of literature following this, proving more and more general results. Okay, switching gears from talking about algorithmic pricing to talking about sample complexity. Uh, so the sample complexity research area really took off with this Stock 14 paper by Colin Roughgarden, which formulated sample complexity in a very sort of compelling way. It asks the number of samples in terms of the parameters of the problem needed to obtain a 1 plus epsilon approximation to the Bayesian optimal mechanism. Okay, and there were some early work studying the single item auction problem. There's been a lot of work studying general single dimensional environments. So where each buyer's preference is a single dimensional value for getting served or not served. And then, this paper was studying a multi-dimensional pricing problem, and there were a number of works studying this problem in more general contexts. A very interesting direction recently is looking at sample complexity for non-truthful mechanisms, which I'll talk about more in the next slide. Cool. So that's sort of a brief window into the, what I think are the salient directions of the subsequent work following this this paper. And now let's wrap up. So there, I think, still some nice open directions that people are thinking about, and one of the ones I think is most tantalizing is combining recent work on the price of anarchy. So analyzing the quality of equilibria in mechanisms that are not truthful, combining that with a theory of sample complexity for non-truthful mechanisms to get, 1 plus epsilon style approximation results. Okay, and this would be combining this literature on price of anarchy for auctions that's been happening recently with this idea of non-truthful sample complexity that I mentioned on the last slide. One of the things that makes this really hard is that truthful mechanisms are nice for two reasons. One, they're strategically simple, but two, if you have data from truthful mechanisms, that data is the true preferences of the agents. Non-truthful sample complexity is difficult because not only do you have to argue about non-truthful equilibrium, but the data that you collect is also non-truthful bids, so you don't even actually know the preferences without doing some work first. There's, I think, a really interesting question of breaking this two approximation barrier for simple item pricings that I mentioned in one of the previous results. And this comes from part of the proof, and I think there's avenues to get better than two approximations for some of these simple versus uh, optimal item pricing questions. And another new recent direction of work that I was really excited to see this recent paper by Kai and Daskalakis is on developing computational methods for very large type spaces. And so most of the algorithmic methods have been for multi-agent mechanism design have been sort of brute force on the space of each individual agent's preferences. And when there are many items for sale, uh, that space is exponentially big in the number of items generally, and so then brute force in this space doesn't seem very compelling. And so what I really liked about this paper is it looked at this idea that, well, look, if there are many items for sale, probably people's preferences are still low dimensional. And so how can we use methods from um, uh, collaborative filtering ideas to come up with good mechanisms in this space? All right, with that, I want to express a tremendous thank you to my co-author Andrew Goldberg on this. I worked on this paper and a number of other papers with him when I was a PhD student, and his vision for the field and setting me off on this direction really was a great start to a career, and it, in fact, I think turned into my entire career over the last 20 years. And so, I mean, it's uh, I guess we've all had influential people on our research careers early in our career, and so just a tremendous thank you to Andrew Goldberg for playing that role for me. Uh, Thank you to the award committee that put the hard work in and eventually chose our paper. And thank you to the entire community, especially the European Symposium on Algorithms community. A paper doesn't get recognized with a Test of Time award unless the community really picks up and is excited about the problems that are hinted at in the paper and continues working and developing it. And and so tremendous thank you to all of the people doing follow-up work in this area, and it's been really amazing to see uh, this all the things that you guys have done. Thank you.